Hi. Today we'll be doing a video on the continuation of linked binary trees, search trees. We're going to do some rotations. So today we will just talk about what a rotation is. So a rotation is an operation on a binary search tree to assist in the process of keeping a tree balanced. So rotation helps the tree stay balanced. Rotations do not solve all problems created by unbalanced trees, but show the basic algorithmic processes that are used to manipulate trees. So we're going to talk about a right rotation, a left rotation, a right left rotation, and a left right rotation. So the right and left rotations are pretty easy, they just go around the root. I think this is from the Java Foundations textbook. I think the right-left rotations might have been a bit off. I'm not sure if the authors had made a little bit of a mistake, but I had to kind of go beyond what they were saying. I kind of had to do it I had to make up my own rotation because it didn't seem like it worked properly. They were still unbalanced. So we're going to start with a right rotation. Can be performed at any level of a tree around the root of any subtree. Corrects an imbalance caused by a long path in the left subtree. So what it is we're gonna have let's just say I'll do it here. So I have a main class. We're gonna use our previous classes, by the way, linked binary search tree, binary tree, no link binary tree, and all that stuff. So see the previous videos to see how we make those classes. So the tree is going to look like this. This is going to be the initial tree. Actually, maybe I'll just do it like down here. So we'll have, oh great, it's my keyboard changed again. How can I change that back? See this works. Okay, yeah, so we'll have a 13 here. It doesn't work on it has to be a specific tree, right? It can't just work on any tree. So we'll have a 13 here, and then we'll have a 7. Then a 15. And here we'll have a 5. 10 and a 3. So see how this tree is unbalanced? Like it should, because a balance means that all the leaves should be within one level of each other. So so let me just get the exact definition of a balanced tree just so that you know. So a balanced tree should have all the, I think it's one level of, within one level of each other. Full and complete are a little different. So a tree is balanced if all the leaves of the tree are on the same level or within one level of each other. Okay, so that's balanced. So this is a leaf because it has no children. This has children. This is a leaf because it has no children. So this is an internal node. This is the root. This is a subtree. This is a leaf. This is a leaf. This is a leaf. So there's a leaf here and a leaf here. So that makes it unbalanced because it's not within one level of each other. This is within one level. And this is within 2 levels. 3 to 15, that's 2 levels, and there's a leaf there. So therefore this is unbalanced. So what a right rotation is we're going to basically rotate. So there's going to be a long path in the left, I think. So corrects. So let's go in here. Let's go in our linked binary tree class. Let's go under find max. Let's see what I have here. So I already have this done. This is from an old assignment, so that we'll do public void. So it returns a void. We'll call it R rotation for right rotation. Public void R rotation. rotation. We're going to say it works with these certain, we're going to say it works with just these integers, or integers like this, like the same kind of, so these are brute force methods, so you kind of have to rotate them, or you could probably code it if they're less than or greater than a certain number, but these itself are just brute force methods, because it's kind of hard to determine what numbers the user is going to use, right? So you kind of have to just do it brute force. Anyways, these are brute force methods. I'm sure you could create an algorithm to keep it balanced if you have certain numbers and each level was a less than a certain number. It can get tricky though, so it's just a brute force method. So we're just going to say it worked with, we're going to just call it tree integers. We'll say it works with 13, 7, 15, 5, 10, 3. I think that's what we used. So here we're going to say, well, what is a right rotation? Or let's just say, okay, yeah, it works with, let's just say integers to keep, or to say ints maybe, so I can fit some more stuff on here. So we're going to have a right rotation fixes, so right rotation, let's just say a right rotation, we'll just call it RR, right rotation, corrects an imbalance of long path in left subtree of the left child of root. So yeah, so just make the, so just get to your classes, access the classes that we made before, make sure you have all that working. So we'll go to, we'll just, let's see what we have here. So we have our definition, we have our tree that we're going to fix, we have these classes that we already made. We're going to see, I'm just going to see, sorry, if there's more definitions that we need here. Okay, so here we go. So these are the steps to do it. I'm not sure we're going to put these steps. So maybe I'll just put them above here. Some doc like. So here, so I'll just say 1. Step 1, make the left child element the root. Make the left child element of the root the new root element. I should probably move this tree down here, by the way. Or we'll just copy it, just so we can see the tree while we're working on this tree. So we'll just put the tree here. So we'll say make the left child element of the root, that's this. Make the left child element of the root the new root element. So we're going to say, okay, we'll shift this. We'll say, we're basically going to put 7 here. So we're going to put 7 at the top, so these are going to get, basically, these are going to disappear. We're going to create some pointers here, so we're going to be like, so I'm going to try to do this on the fly, even though I already have the node set up. So basically, we're going to say, we're going to create a pointer here, so we're going to say, what should we call this? Temp root. No, this is going to be a new root. So we're going to, let me just finish the steps. So first we're going to make the left, actually we can do the steps in order. So we'll say, okay, so the first step is make the left child element, that's this. The left child element of the root, so here's the root. Here's the left child element, that's 7, the root's 13. So we're going to say, okay, make 7 the new root. So we're going to say, we could just say root dot left, root dot get left, right? So perhaps we're going to need a pointer here, because if we go root dot get left, right? Root dot get left. So we're gonna so if we say root dot set, so we could say tree. What the heck happened there? So we'll say tree dot. Do you have a set root? Tree dot root points to root dot get left. I mean, I'm sure that's a way to do it. What's this here? Cannot find symbol tree. Okay. Whoops. So tree dot root. Where's our tree? Our tree is in main. So maybe let's just use the root. So let's just set a pointer here. Let's be like binary tree node of type T. We'll say current node points to root. So we're going to, what's the root right now? It's 13. So we're gonna say that, and then we'll say we're gonna create another pointer here. So let's just comment these out for a sec. So we'll say, okay, current node points to root. Then here we'll say, okay, well, binary tree node of type T. We're gonna say inner node points to current node dot get left. So we're gonna say, okay, well, so current node points to root, so current node points right there. We're gonna say, okay, not inner node. Inner node points to current node. So current node is root dot get left. So we're gonna say, okay, well, inner node points to the current node, which is the root dot get left. So there we go. Do we need a set root? Okay, so what we can say here, actually, we couldn't use a set root. We could make a set root. Or we could say, root points to root dot get left. I haven't done this in a while, so I'm just kind of like, okay, well, how did I do this before? So that's the problem with coding. If you don't practice it regularly, you can forget. Like, not everything, but you can forget what you did. But here we have a 13, so we're gonna say, okay, well, that's our root. So we're gonna say, okay, well, root. So there's a root here, and we're accessing that because linked binary search tree extends linked binary tree. So our root should be in here, and we have access to it because it extends. So we have access to the variables. So sorry, let me just grab some water here. My head's kind of getting dry. So we're saying, okay, here we'll create two pointers. We're gonna create two object reference variable pointers. One to the root and one to the inner node. I don't even know if we use these so far. We have them. So we're gonna say, okay, well, the root points to root.getLeft. So root, which is 13, points to root.getLeft. So there we go. This is the root now. So I'm pretty sure that the 13 and 15 are currently, they're gone. They're gone at this time. So that's, so we completed the first step. Make the left child element of the root the new root element. So that's our tree now. So right now our tree just looks like 7, 5, 10, 3. So the next step is, what's the next step here? So I was going to say, okay, well, I think I did this with a lot of trial and error. It may have taken me a few hours to figure out, or maybe at least an hour, something like that. That usually happens. You're going to try things, they're not going to work, and you're going to keep trying it until it works. So you're going to say, okay, make the former root. Excuse me. So make the former root element the right child element of the new root. So we're going to say, okay, make the former root, so that's 13. So we're going to need a pointer to the former root, so we're going to have a pointer here. Binary tree node of type D, current node points to root. Make the former root the right child element of the new root. So, okay, so we completed step 1, right? So we have 7, 5, 10, 3. So make the former root element the right child element of the new root. Make the former root element, which is 13, the right child element of the new root. So we're going to say, okay, well, root points to root dot get left. Then we're going to say, okay, well, root dot set left to current node. I'll just check if that was what I did before. I say set left. Make former root element the right child element. Okay, so this is set right. My mistake here. So set right. So that's correct. So we're gonna shift the root first, right? Root points to root dot get left. So we're gonna say, okay, well, the global root of our binary linked binary search tree is going to set its root to the current root dot get left. So that's our root here, 7 now, 5, which has 5, 10, and 3 in the tree. Then we're going to say, okay, well, maybe so I should do like our current tree, at least what I think it is. So it's actually no, it's 7. So it's 7, or sorry, so I have a little bit of a stuffy nose, I'm not sure why. So 7 is our root. Then we have 5, then 10, then we have 3. Then we're going to say, okay, we'll set the right, we're setting the right child of the root to the current node, right child of the root. So set the former root element, make former root element the right child of the root. So it basically it's going to put the whole tree here, I think. That's going to be wonderful. So we're going to say, okay, we'll put, let me just make sure that's exactly what it's saying here. So make the former root element, let me just make this proper. Make the former root element the right child element of the new root. So make the former root element, that's 13, the right child element of the new root. So yeah, that's going to put the whole tree here. Okay, so we're going to have $13 right here. We're going to have to change the whole tree here. So let's just take that, because that was our current tree. So let's do step 1. Then we'll have step 2. And we'll be like, okay, we're going to follow this directions, make the former root element the right child element of the new root, make the former root element the right child of the, so we're going to take this whole tree here and put it here. Basically that's what it's saying. So we'll say, okay, we're going to put a 7 here and a 15. Might move that over a little bit. 7. Maybe not. It's we'll just work with that. So 7, 13, 7, 15. Then we have 7 has 2 children, 5 and 10. 5 and 10. And 5 has 1 child, that's 3. Whoops, need some. Great, it's gonna get shifted over now, wonderful. So 5. And so 7 has 2 children, 5 and 10, and 5 has 1 child, that's left child is 3. Okay, so that seems to be done. Obviously, we're like, well, what the heck's going on here now? We're probably gonna have to set some of these null here. So back to the code. Where's our code? Up here? Root points to root.getLeft. Root.set right to current node. Current node. What is current node points to the former root. So what do we say here? Root.set right to current node. Then we're going to say, okay, well, current node, which points to that 13. Aha, okay, we're going to set left to inner node. What's inner node? Current node.getLeft 7. No. So initially, current node points to root. We're going to say, oh, well, inner node points to current node dot get left. So inner node points to current node dot get left. So it's this whole thing here basically. 7, 5, 10, 3. That's what we said. So then we're saying current node, which is a root. Saying current node, which is a root dot left child. Set it to current node dot set left to inner node. So we're gonna go back here. We're gonna say current node dot set left to inner node. Inner node. I feel like something's not right here. So we first have our binary tree node, points to the root of the tree. Okay, so then after that we have binary tree node inner node, point to the current node dot left. There, 7, 5, 10, 13. Then we're saying, okay, well, root points to root. Root points to root dot get left, so we just have 7, 5, 10, 13. Then root dot set right to current node, which is 13, so we put the whole tree there. Then we're saying, okay, well, current node dot set left to inner node. What was inner node? It was current node dot get left. Current node points to so inner node. So current node dot set left to inner node. Current node, which is the root here. Dot set left, so set this left child to inner node, and inner node was originally current node dot get left. So I think it seems like it was the same thing. Is that the exact directions? This was the right route. So 7, so we have 13, 7, 15, 5, 10, 3, so or the direct, sorry, did I even put the step 3 on here? So we have here, let's just change that here. So let's just say step 3, make the right child of what was the left child of the, this one's a little tricky, former root, the new left child of the former root. So we're saying, okay, we'll make the right child bring that up here, bring that up so we can see it hopefully while we're reading this. So make the right child of what was the left child of the former root. So the right child, so 10, the new left child of the former root, the new left child of the former root. Yeah, that should be right. So we should put a 10 here. So 10 should have just gone here. So is that the final tree? 10, this should be gone. So how many elements do we start out with? So we had 1, 2, 3, 4, 5, 6 elements. 1, 2, 3, 4, 5, 6 elements. Is that the final tree? So we have a root. So here's a root. Is 5 less than 7? It is. Is 13 greater than 7? It is. Is 5 less than? Is 3 less than 5? It is. Is 10 greater than 5? It is. Is 10 less than 13? It is. Is 15 greater than 13? It is. So these are the numbers. There is 13. Are they the numbers? 13, 7, 15, 5, 10, 3. Yeah, so this is it. So why is my code wrong? So we're saying, okay, make the left child element of the new root element. Make the left child element of the root the new root element. So we're going to say, okay, we'll shift 7 to the right. Then we have, so make the left child element of the root, that's 7, the new root element. So there we go, we have our first step. Then make the former root element the right child. So we're going to need a pointer here to the root. Make the former root element, which is 13, the right child of the new root. So we're going to say, okay, well, I probably should have made a second tree here, but we're going to just double up here. We're going to do the thing again. So it's going to say make the former root element the right child of the new root. So we're going to put the whole tree here again. Make the former root element the right child of the new root. Yeah, so we're going to put the whole tree again here. So 13. Then we're going to have a 7. Then 15. Then 7 has 2 children. That's 5 and 10. 5 and 10, and has one more child. That's 3. So there we go, the step 2 is done, and it's saying, okay, well, make the right child of what was the left child. Make the right child of what was the left child of the former root. So left former root, so that means a 13, I think. So make the right child of what was the left child of the former root, the new left child of the former root. So I think inner node was wrong. Inner node points to current node, dot get left, dot get right perhaps. Did I mess this code up on my assignment? Hope not. Dot get left. So you see what we're doing here? We're saying, okay, well, inner node is the current node, which is 13. This is a little, what's that word? Riddle? Seems like it's like a riddle. It's like, well, what? It's kind of like the wording. So it's saying, okay, well, the inner node is current node, which is 13. Well, sorry, which is the root. Because we're doing this initially, so nothing has changed. So we're saying we're taking this one. We're going to start with the initial tree. So we're going to say, okay, well the inner node is current node, which is 13. Dot get left. Dot get right. Because that's what we need here to change the inner node at the end. We need a pointer to that inner node. So now it's saying we'll make the right child of what was the left child of the former root. So here's the right child of what. Make the right child of what was the left child of the former root. So that's the initial tree. The new left child of the former root. So here's the former root. So here we're saying root dot set right. Sorry, current node. We're saying current node, get to the former root, set the left child to inner node. So we're saying, okay, well, look, I apologize, these should be swapped here. That was step, this is initial tree, this is step 1, step 2, and then step 3. So we're saying, okay. Take a pointer to our inner node, then we're saying at the end, make the right child of what was the left child of the former root. So this, they're referencing 10. The new left child of the former root. So here's the former root is now down here. So we're saying, okay, we'll place 10 here. So that should be right. 7, 5, 13, 3, 10, 15. So is my old code wrong, or was I looking at the wrong place? Excuse me. Actually, no, it was right. Sorry, I didn't see the last part. So it has, okay, binary tree node, current points to root. Hopefully I'm not confusing anyone and you understand. So I apologize if I'm confusing anyone. Hopefully this clears it up. So binary tree node of generic type T. Inner node points to current node dot get left dot get right. So this is a method chain here. We're saying the take a pointer to the inner node. We're going to take a pointer to something, we're going to name it, to the current node, which is the root, dot get left, which is going to traverse to the left subtree, and then dot get right, so from there it's going to traverse to the right subtree. So then saying, okay, well root points to root dot get left, shift the root. We could have maybe done this differently, reference our tree, and said, okay, well tree dot root dot, we could have said that too maybe. Whoops. We can't access our tree at the moment because we haven't instantiated an object, but if we did, maybe we could access it. We're just saying, okay, well root dot root points to root dot get left. So we're going to shift the root, then we're saying, okay, well root dot set right to current node. Then we're saying, okay, well current node dot set left to inner node, and then return. So that the return is just, you don't need the return, it's just extra. So it works. That should be 100% correct. So we'll scrap these trees now because we're done. Actually, we're using the same trees. I think we are using the same. Actually, we'll just rewrite it. So hopefully that helps. Actually, I think I will take a little break and I'll come back. So I'll see you guys in a few minutes.